okay, now we're coming back to the parallelization. Yeah, and I told you for efficiency, we have to make sure that we take the data and the work and everyone gets the same amount of work. So everyone is done at the same time and we're not wasting that some people are done early or have a coffee break in between. Yeah, and if it's not working, it's called load balancing. And the problem is, for many cases, I know the data I get and have some idea how complicated the calculations are, but they can change over time. They can depend on the numbers. And so sometimes you don't know exactly how it's happening. Yeah? So basically here you say, okay, I have my hole, I take the same number of people in every hole, and then they start digging, and they go like 1 meter deep, and then, oops. Yeah, and in there's sand, so these guys can go very quickly. Here is rock, yeah, or here's mud, and so they go quickly, they take very long, and then so some time they say, okay, like the sand people are lower, so move some people over here, yeah, and then basically after another meter, it's different, so you have to move the people back, and the same thing can happen in your calculation. Sometimes it's easy and all processes go in the same speed, sometimes not. Then you have to stop, basically say, oh, how far you are. And if it's unbalanced, you say, okay, then I take a little bit more of your data and so on. But when you have to exchange it, this is also slowing down your processing. So meanwhile, the idea. Yeah? So the basic idea of parallel computing is not complicated, but basically synchronizing and make sure everyone is going at the same speed. Exchanging the data, that everyone has the data he needs when he needs it. This is basically the complicated portion. Okay. Okay, so now we need a little bit to talk again about the computer, because I showed you this very simple picture of a computer, but it's actually not that simple. It's a little bit more complicated. So there is one type of computers which are called distributed memory. Yeah? So you have, like here, you have a processor and it has a memory, and then it's connected to a network. But basically, so this processor can read this data, but cannot read that because it's the memory of the other processor. So basically, if that one needs data from here, he has to tell that somehow that processor, oh, I need this and this data, and then that processor sends that data over network to the other one, and then he can calculate on it. Yeah. This is basically how when you do parallel computing here. So, what is the advantages of such a system? Because this is basically a board you can buy at the hardware store, a processor with memory. It's like a laptop. So each of them is cheap. You just add them in a big box, get enough power in, you make the network, so you can make very, very large computers out of it. Yeah, it just depends how much money you can buy, how much processor memory pairs you can buy until you run out of memory. Yeah, and you need also a little bit money for the network. But there is no limitation here. So we have computers with, this is typically called a node, and we have now computers with 100 to 500,000 nodes. Okay. And also, yeah, I said you read here into the cache, because reading here from the memory into the cache is totally independent of that one. So also this caching effect is totally independent. So this is also very simple. So this is the advantage. The disadvantage is now, as I told you, if I want to have data from the other memory, I need to somehow get it. And this is, so I have to communicate with the other processor, and this is called a message. Yeah, I send them, like on your smartphone, an SMS or chat, you send a message to someone else, say, I need this. And then basically one sends, I need this, and then the other one sends it back, says, oh, here it is, it's 5, or it's 10, or whatever. So when you write the program, who is doing this sending back and forth of the messages? Or who is saying when to do that? You as a programmer, because the computer is stupid. It doesn't know when to do. So here you have to know to tell, calculate, oh, now you're here, you better send this value to that processor, or you ask that processor to get it. So you have to think about when do they need the data, when do they send messages, when do they need the value, and you have to put these extra instructions for these messages into your program at the right place. If you do it too early, it's probably not a problem, but if you do it too late, the other one is waiting and is wasting time. So this is called explicit communication via messages, explicit synchronization, so you have to talk to each other. Is everyone done? And explicit means you as a programmer has to write the program commands to do it. And you also have to think about, yeah, my data, what data goes in this memory, what data goes in this memory, and what goes in this memory. This is the data distribution. So you as a programmer do that. Yeah, so you have not to write only the program, but you also have to say how the data is distributed, how every processor is doing which work, how to communicate, how to synchronize. A lot of stuff. So, as usual, yeah, you get a cheaper computer, which can go very large, but when the student who has to write the program has to do much, much more work. Yeah, and this is how the compute centers are working. They get cheap computers, and then they hire all the cheap students to do complicated work. Welcome to HPC. Okay, and then there's different ways of doing it. Of course, we're sending these messages, but luckily over last, I think it started in '92, it's a while, there's standard ways. So it's something called MPI, Message Passing Interface. It's a specific doing that, and we learn that perhaps like at the end of a session or tomorrow. Okay, you could do it in a different way. Yeah, you could do it this way. You say, I just take one large memory and then take a collection of processors and I put the network in between. So now every processor through the network can read all of the data and you don't have to synchronize. Yeah? So you just split up the work between the processors, but you don't need to think about data synchronization. You don't have to think about sending messages. You just, yeah, it's much simpler. Yeah? You still have caches, so you somehow need to, in this way, have to synchronize the caches. So like if someone is reading the data, and when someone else is writing a new value, you have to make sure that the cache, that value is thrown away, so that next time you're reading it, you're not getting the wrong value from the cache, but the new one from the memory. So it's more work, but it's on the hardware. Again, there's a standard way of doing like this, and this is the standard way here. It's called OpenMP, and we learn that also tomorrow. You can also use MPI. You can just ignore that you have a global memory. Yeah, you just think about every processor has a portion of it, and then an MPI program would still work on that system. Yeah, so MPI works on any computer, whether it's distributed or shared, but OpenMP only works on computers who have, it's like limited, yeah, which only has one memory. I have to say, when you really open the box and you look into it, it's separate memories. Like it's like a chip with a block of memory, another chip with memory. But the idea is basically for the programmer, yeah, it looks like one big memory. So the hardware make it look like it's one big block. Yeah, it's logic. It's in reality it's distributed, but for the programmer it's like virtually like one big block. So what are advantages and disadvantages here? So advantages is this global address or this big block of memory is very programmer friendly, yeah, because just take your data, put it in there, done. No thinking about data distribution, no nothing. And it's easy to program, yeah. You also kind of communicate. Basically, one process is writing into the memory, and the other one is reading the data. So you don't have to messages. It's just based like one is writing, the other one is reading. It's very fast. Well, you only have to, and the only is in quotes. You only have to make sure that you're only reading after the other guy was writing it. And you don't know because it's another processor, yeah? So you still have to talk to each other. Oh, I put it in memory, now you can read it. So this synchronization, you still have to think about it. Yeah? You have to make sure that you're reading that value only after writing, but the communication and the data distribution you can forget. The problem here is with the synchronization, if you forget it or you don't, you forget to tell the other one can still read the data, but it could be the old value. Yeah, and so you don't get an error or you don't notice. Yeah, you just get the wrong number, and you do like hours of our calculation with wrong numbers. And at the end, you know, so why I have storms all over and it's not nice weather. So, and the problem then is, in such a program, finding the spot where you forgot to put the synchronization, this is a really, really tough problem. So it looks a little bit simpler, so you are quicker in programming and get it working, but if it's not working, it's tougher. Okay. The disadvantage is, yeah, you have to put a lot, like this, like let's see, getting back to a picture. Because all these processors want to work to the memory all the time. You're reading a lot of data. That network here is very expensive because it has to handle a lot of reading and writing. So you need very expensive hardware for scalable access, and you need extra hardware for doing this cache coherence, that basically that your caches don't get messed up. So people found out over time, yeah, like if you say, I want to get such a nice system, but I don't want to spend too much money on it, yeah, you typically get computers of that sort between 10 and 128 or something, 1 to 64. Yeah. So when you look at your laptop or your smartphone, yeah, it has 6, 8, 16 processors, 1 memory. So this is basically a shared memory system. And you can use it this way. But as soon as you're plugging multiple smartphones and multiple laptops together, you are distributed. Of course, what happens? Yeah? So people need larger and larger computers. So what they do is say, I have a computer made out of multiple nodes. And when each node is a shared memory. Yeah, so I take a many core, so I take a server processor who has like 64 processors, lots of memory. So this is a shared memory system. And when I connect them together with a network, so this is a hybrid computer. So it's a distributed computer made out of shared memory computers. Yeah, and basically, as soon as you have 2 nodes, all computers are typically of that size because unless it's an embedded market or some fitness clock or something, every processor has more than 1 core. I guess even your fitness clock has more than 1 core. So this is basically how a typical system today looks like. So you have, inside you have this, you can use the shared memory, but between these nodes you have to use this distributed MPI. That was the state, when was it? Say 2010, 2015, I think. And when some people think, oh, it's not fast enough, we need more power, we need more performance. How can we get more performance? Yeah, we cannot add more nodes, it gets too large. Then they realize many processors have graphics cards. A graphics card is actually for basically making nice pictures on the screen, but in order to make these nice pictures on the screen, you have to do mathematical calculations. You do transformations and projections and so on, which are matrix operations. And when you say, oh, our simulations for weather, it's also projections and calculations. So we said, hey, yeah, I have this graphics card anyhow. In addition to using the main processor, I also use these graphics cards to do even more calculation. Of course, this graphics card were never built for normal calculations. They were built for doing graphics. But people found a way to kind of say, I want to do this and this mathematical calculation, how to express it in a way that they run on a graphics card. Yeah? And yeah. So this is basically what I'm talking about. Yeah? So people are using these graphics processing units, GPU for general purpose computing graphics cards, and they are used in addition. Also, inside the processors, people added so-called vector units. So instead of say I'm adding two numbers together, I take like 4 numbers, so much space in the CPU. So this is typically 4 numbers at the same time or 8, but it's also like extra hardware to do a lot of calculation at the same time. So currently you have processors with many cores, special little vector units, and graphics cards. So when you look at the, and a graphics card, when you actually open up a graphics card, or you can, or look into the documentation, this is a little parallel computer by itself. So basically, again, you have your memory, and then you have stacks of little processors, basically who can run at the same time. So, but the difference is, like with little thread processors, they can do the same thing at the same time, but not different things. Yeah, so all of them do an add, and all of them do a multiply, synchronized way. So you have to program in a specific way that everyone is doing the same thing, but basically it has multiple of these, which can work independently. And this is called single instruction multiple threads, SIMD mode. But again, it's like a little parallel computer. So basically, to distinguish what is a CPU and a GPU, you can compare it a little bit to a car and a bus. So you need to transport, like the school, downtown. You can basically take, okay, I take 10 cars, each car takes 4 people, and it can go much faster because it's a car. And when it doesn't fit, cars have to come back and pick the next batch. Or I can take like all of them in one bus. The bus cannot go on very slow, but also it get there. So if you have lots of stuff and you have to go, not so far, like buses are better. So some stuff is better for CPUs, like small things and so on, and then you have to do lots of calculation, it's better to use the GPU. But the best thing is basically do it at the same time. So how does a computer currently look like? At least a high-performance computer. So you have multiple nodes. Each node has multiple processors, many-core, multi-core, and it has a number of like graphics cards, 1, 4, 8. And then basically a processor, I told you, is a multi-core processor with multiple caches, and each of these accelerators is this little parallel SIMD processor. So a current parallel computer is a parallel computer built out of parallel computers, built out of parallel computers. This is where we are, unless some crazy guy has yet another idea how to make it more complicated. Okay, and I have these blue boxes which says network, but this can be like a connection, what we call a tree, like it's spreading out. It can be like a a mesh or a torus, or like the Fukaku is a 6-dimensional torus. I have no idea how a 6-dimensional torus looks like. But basically every process is connected in 6 dimensions with something. 3 dimension everyone can handle, but 6, I'm lost. Yeah, and then you can have your disks in every node. You can have storage at the network, yeah, or you have some far away, yeah? So this is basically how complicated a high-performance supercomputer looks like. So, and I told you, your job is to write a parallel program, or at some point, which means not only you have to distribute the data to the memory, the work to the processors in the most efficient way, but now you have to also say, okay, memory means I can put it in this memory, I can make sure it's in the cache, or is it in the memory of the GPU? Again, how much do I put here, here, here? So it's not just, oh, I take the storage and every processor gets its slice. No, you have to think about which data needs to go in which portion of your computer. And then again, you have to think about which portion of a calculation is having in a vector unit, in your normal processor, in the GPU, how they work together, and it's still going fast. They don't communicate too much, we don't synchronize too much, and you're done the most efficient way. Yeah, so this class would have been much simpler 20 years ago, but unfortunately you got born a little bit later, so you have to deal with that thing. I'm sorry. Okay. Yeah, and then you wonder basically how large the systems are. So here's some numbers, and so basically, so there's a list, because people in the centers like to brag about how fast your computer is. So you measure a specific program called high performance linpack. You get your number of floating point operations, and then you send it to someone and he makes a list. And he basically, the 500 fastest computers get published in a list. Yeah, and then I say, oh, I'm number 25. And you do that every half year. And this is done for many years. So I have only the data here from 2000 to 2024. And it basically says the largest system, how large is it? So in 2000, it was 10,000 cores. And now we are up by 10 million. But it's the largest system. We say, okay, there's these very expensive government systems or things. But say, even if you say you take all 500 and you take the average or median, so we are now, like even the mean average system is about 100 to 2,000 cores. Yeah, so if you want to say high performance computing, I'm working on the 200 fastest 50 computers in the world, so you have to make your program run on average on 300,000 processors. Yeah, and even you say, okay, yeah, I'm just a small university, we only have number 500. The smallest computer in top 500 still has 10,000 cores now. Okay. Very quickly, let's see, I started at 3, isn't it? So I have until 4:30. No, at 3:30 I have until 5, yeah? That's right? No, I started 3:30. Yeah, I have until 5. Yeah, yeah. Okay, okay. Yeah, yeah. Let's see. Okay. So how does that look like? And I show you some examples. And this one, unfortunately, you can't see anymore, because now we put a quantum computer in here. So it's a kind of a waste for that chapel. The real computers were much nicer. So this is Barcelona, where Fabrizio is from. And when they put the computer, you have to correct me, but this is the story I know, is they had to do it very quickly. They couldn't make like a special building. So they were looking around on the campus. There was an old church. It wasn't used as a church anymore. So they used the church and basically put the computer in there. And in order not to need to cool the whole church, they put it in like in a glass metal box. So they only have to cool like this box. And it's amazing. You go, or it was amazing. You go in there, and it's this church in yellow, orange stone, and they have this red carpet, and you have this cold metal in the middle, and it's like the altar of computing, and it was, I mean, it's just, everyone was standing there, oh.
Now there are 3 quantum computers on the front, and on the back very
Yeah, but it's, yeah, it's like 3 boxes, you cannot even, don't blink, it's...
we removed the full ceiling, so now you can see the real.
I like the red one. Okay, but yeah, it was not just my opinion. There was a kind of a competition or whatever. People can vote, and it was voted the most beautiful data center in the world in 2017. They have, like, even the new facility is very impressive. Okay, then RIKEN. But this was not the current computer, Fukaku, but that was the K computer. It was the one before. It looked like this. And it had like 864 racks. Like a rack is one of these boxes. In each box you have multiple of these nodes. And there are some numbers, basically. One number, how quick can it go in theoretically, and how fast did they calculate this LINPACK performance benchmark. So at some point it was number 1 in the world, and in 2019, over 8 years, it was only spot number 20. And then there's some notes and other information. Oh, man. And I probably also will see that there's actually a small model in the first floor. So the building is actually 4 floors. In the upper floor, you have a computer. Below there is the cooling for the computer. Then in the second floor, the disk system. And in the first floor is the cooling for the disk system. So all this white box here on the left side is that computer. At some point, it had its own train station. But when we got Fukaku, they had to rename the train station. And now it's a different name. It doesn't say Fukaku main station anymore. I think they say it in the train, but it's not written on the wall anymore. The interesting one is, because we're in Japan, yeah, there's a lot of earthquakes. So what you do is basically you take this whole building, it's one big block, and then you have kind of like a box down here, and the whole building is put on specific earthquake dampers. Like the whole 4-story building with all this weight. And if you go down in the basement, so this is how it looks like. You have, it's about, my height is like 2 meters. And then you have dampers like this, and this. So this is like rubber. So if the earthquake is doing like, whoa. And then basically this is for if it goes up and down. And then these are for side movements. Yeah. And as far as I know, the building can withstand a 7.5 earthquake. So it's not just basically taking a computer, make a building, put all the cooling there, but all of that extra stuff. Yeah, and this is why not everyone in this garage can have a supercomputer. Yeah, it's a lot of work. This is a system from China, 2013, which was number 1 at that time. It had already like 61 petaflops. This is 2018. This was one of the first computers now with graphics cards. So each node had 2 Power 9 processor from IBM. This is Fukaku, and as far as I know, you will see it on Tuesday, if you can stay all the way to the end. Yeah, this is again, it doesn't have GPUs, it only specific ARM CPUs, but many of them. So it has 185, almost 189,000 CPUs. And each has 48 plus 4 cores, so it's over 8 million cores. This is number 2 currently. This is in Oak Ridge, the Frontier system with EPIC CPU and AMD GPUs. This is number 1 currently, the most powerful computer now. It's called El Capitan. It's in Lawrence Livermore National Lab in US. It has, again, EPIC processors and AMD Instinct 300A processor. So in May I have now, as a LINPACK measurement, 1.742 exaflops, almost 2. This is the current record. And then basically this is an example of our computer in Jülich. with basically the latest. It's on the, like, as we are speaking, we try to make it fully functional. We made the Linpack run, and we got exactly 1.111 exaflop. And so we are number 4. Yeah. The interesting portion, it's not a special building, so it's made out of containers, so we could do it very quickly, and you see all the cooling on top. So we try to do it with the least amount of money and as simple as possible. It works, almost. Okay. In case you said, like, okay, Fukaku you will be able to see, but not everyone can go to all these places. A few of these people took the time to kind of scan in their system with cameras, and then they are websites you can go, and then you can, on your computer, you can walk through it, and you can turn around and look at it. It's really cool. So I have here Mare Nostrum 4. You can even walk in the chapel, Summit, Fukaku, and there's even a second one where you can go into the basement and see the earthquake dampers. And then there's also, so this is with real pictures, and we have one just, it's a computer-generated one, but you can also go through our facility. Okay. So, what is the most important things you should have learned in the last more or less like, say, 45 minutes to an hour? Yeah? So, how does a current computer look like? It's distributed nodes, up to 200,000, connected via high-performance network. Each node has many core processors, a node shared memory, like a shared memory system inside the node, and 1, 2, 4, up to 8 accelerators. They all run basically Linux. Why don't they run Windows? Because Microsoft wants that you buy a license for Windows for every core. So you have 1 million cores, you have to buy 1 million licenses. So no one wants to waste their money, so everyone is using free Linux. And then it's not like your laptop where you can basically sit in front and say, oh no, I just run on that computer, because there's like hundreds or 1,000 people who want to use it at the same time. And so it's more like you compile your program and said, okay, here's my program, here's the data, and you give it to some sort of system, and that system basically, it's your time, basically it's run it for you, but it can take a day. Yeah, so that's basically how it's currently working. But we see how this is working tomorrow in the practical exercise. Yeah, you have to do exactly that. Okay, but as I said, it's high performance computing. It means the ultimate goal is do it as quickly as possible. Yeah, and otherwise you are wasting a lot of government money, and a lot of people get angry if you're wasting money. But the basic principle how to get so fast is just extreme parallelism. You use as many processing units as possible, you use as many memory blocks as possible, and then you can do a lot of things at the same time. So the basic principle is simple, but when you really need to program that, and unfortunately as a programmer you are responsible for doing all that, it gets a little bit more complicated. Okay. End of first lesson.